Hello, calculus type people. Hope you're having an amazing day today. Today we are going to be talking about the other third of calculus. Now, up until this time, we've talked about two major calculus topics. One was limits, and the second was derivatives. So today we're going to be talking about antiderivatives. Now, antiderivative is kind of a harsh word for it, but it really describes what we're doing. Antiderivatives are the undoing of derivatives, or kind of taking a derivative and going back to a function above that. And what we call those are integrals. All right, we call them integrals. So these two words, antiderivatives and integrals, really in either place. You could say an antiderivative, or you could say an integral. So you can use both, and to really explain what an integral or an antiderivative is, we're going to look at a couple of examples here. First off, you've got 4x cubed plus x squared plus 5. And what we're going to do is come up with the derivative of that to kind of look at the process of working backwards. Now, quick note, I told you again earlier, I don't have the notes for this one printed out. I do apologize. So you may want to pause the video really quickly and just kind of get down this part right here. You may want to just write this part down really quick, and then we'll move on, and I'll give you the rest in just a second. So again, pause the video if you need to, and go ahead and write down this stuff right here. All right, so for example 1, the derivative of 4x cubed, you bring your 3 down, 3 times 4 is 12, x squared. So we subtracted 1 from our exponent, and we dropped the exponent down and multiplied it together. Now, the derivative of x squared is 2x, the derivative of 5 is 0. Over here, the derivative of 4x squared is 4 times 3, 12x squared. Excuse me, I said squared and it's cubed. 4x cubed is 12x squared. Derivative of x squared is 2x minus 3, so the derivative of 3 is 0. Now, because of this, if you started with this guy right here, let's say that we started with him and we wanted to go up to this guy. We started here and we want to go up to this. Okay? So therefore, if this is the original, 12x squared plus 2x, then the antiderivative of this guy, f, is capital F, 4x cubed plus x squared plus c. Now this c represents just a constant, and we'll get to what it means here a little bit later, but it's just some constant number. Okay? So I want you to kind of think about this. What would it take if I have f of x, what would it take right here that if I took the derivative of this, I would end up at 0? The derivative of what is 0? Well, the derivative of this to get to 0 would be some constant, right? Some value for c, like the number 1, the number 5, the number 42, whatever. It's some constant c. The derivative of a constant c is 0. The derivative to get to 1, the derivative of what is 1? Well, the derivative of 1 is 1x, or just x, right? The derivative of this is 1. So now we get into what about to get to x? If this is the derivative, what would the original look like? Well, you know it's going to be raising 1 on your power, right? But we can't just raise 1 on the power because the derivative of this is 2x. So we need to compensate with the 2 that we are missing. So again, the derivative of x squared is 2x, not just x. So what I'm going to do is divide it by 2. So if I take the derivative of x squared over 2, I get 2x over 2, which is x, right? The derivative is 2x over 2, which is x. That's where I get that. Okay, so if the derivative is x squared, we know we'll have to go to x to the third. But again, the derivative of x to the third is 3x squared. So I'm going to compensate by dividing by 3. The derivative that gets you 2x cubed, the antiderivative of that is going to be x to the fourth, and again I have to compensate with that 4. So again, the derivative of x to the fourth over 4 is going to be 4x to the third over 4, which is just x to the third. So really the process here is x, if you have x to the n, then your antiderivative is going to be n plus 1. Look at what we've done here. If this was n, we added 1, divided by n plus 1. So whatever the n was, like for this example, n is 3. So it's x to the n plus 1 over n plus 1. And that's how we came up with this guy right here. It's the integral. This is your antiderivative formula. Okay? Now again, this is a spot where you want to pause and write down this next section right here. So pause and write down that section. So this is talking about the indefinite integration. This is a synonym for an antiderivative. An indefinite means that you are, it's going forever. So you're going to find the integration or the integral of an entire function, not just a piece of it. A small piece of it we would call a definite integral. But this is called indefinite integration. And it starts off, just a little naming here. This big, long, stretched out S-looking figure is the integral symbol. F of x, the function you're integrating, is called the integrand. D of x, this is the variable of integration. This is with respect to x, kind of like when you took the derivative with respect to x. This is where that comes from right here, the dx. So the integral, or the antiderivative of f, ends up being capital F plus c. And capital F comes from this guy right here. C is called that constant of integration. Everything is plus c. So it reads the antiderivative of f with respect to x. The antiderivative of f with respect to x. Remember, like dy dx was the derivative of y with respect to x. This is the integral of f of x with respect to x. All right, and then a couple of basic rules here. Take a second, pause the video, and write down those basic rules. All the rules. All right, so let's talk about them. This is the integral of 0. Well, just like we saw up here in the table in the top, the integral of 0 is some constant, right? Well, what if you already have a constant here? K represents just a number, like 2, or 3, or 42. The integral of a number is that number times x plus c. Right? It's that number times x plus c. Down here, the integral of 1 is just x. Remember, that's 1 dx right there. It's just x plus c. See how all these have a plus c on them? And then 4 and 5 are just how you can distribute the integrals. So this is the integral of k times f of x. This is a coefficient times f of x. Then you take the derivative, or excuse me, you take the antiderivative with k on the outside. What this means is that if you have a coefficient k, you can just pull it outside the integral and rewrite it, and it's the same thing. So if I have a factor that I can pull out, like a greatest common factor, then do it before you take the integral. That's all that's saying. Number 5, if you're adding or subtracting two functions, then you take the integral of the first one, adding or subtracting the integral of the second one. There's really not a lot to go off of there. It's just very, very simple. The integral goes here and here. And number 6, this is the one that we like to hang around. Number 6. It says the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c, where n cannot be negative 1, obviously, because you can't have a 0 on the bottom. So the integral of x to the n dx equals x to the n plus 1, n plus 1 plus c. N cannot be negative 1. All right. So again, those are just a few of the a few of the different relationships that we have with integration. Really, the best way to do these is to try them. It's the best way to do them. So, start by writing down example 3. Again, if you need to pause it, feel free. Go in a little bit here. We have the integral of 1 over x squared dx. So, first thing I'm going to do is rewrite this thing as the integral of x to the negative 2 dx, because I can do that. That's okay. I want to try and get this thing up into the top if possible. I don't want to ever deal with denominators if at all possible. There is a way for doing it, but I want to try and avoid it if I can, so I'm going to. Okay, so again, remember, it ends up being x to the n plus 1. So if I add 1 to that, what's it going to be? Well, it's going to be x to the negative 1 over n plus 1, negative 1. Remember, n in this case is negative 2. And then plus c, plus some arbitrary constant. Now, I don't know what c is. C could be anything, right? C could be absolutely anything. Later on, we'll figure out how to find out what c is. But for right now, it's just anything. Now, I know what you're saying. But Mr. Ballard, this can't be negative. Raw, what's going on? And that is true. So I'm going to take this down here. That's going to be negative 1 over x to the positive 1 plus c, which is just negative 1 over x plus c. Never want to leave a negative exponent. Okay? Example 4. Go ahead and write that down real quick. Pause it if you need to. The integral of the square root of x plus 1 over 2 square root of x dx. Notice where the integral started. I've had questions before as to where does the integral stop? Does it stop here? Because it has a plus sign, so it's got to stop there, right? No, it stops whenever you have your dx. So it's the integral of all of this. So the first thing I'm going to do here is rewrite it as the integral of x to the 1/2 plus, and I don't like this, so I'm going to call this 1/2, 1 over 2 x to the negative 1/2. Because I don't like dealing with square roots personally. I think they're a mess. But that's neither here nor there. Dx. So the first thing I'm going to do is rewrite it. Let's come underneath here and see what this is equal to. X to the 1/2. So add 1 to that, and it's going to be x to the 1/2 plus 1 is 3/2. Now you have to do over n plus 1 over 3/2. Now you know we're not going to leave it like that, but we'll get to that in a minute. Plus 1/2 plus 1 up here is going to be x to the positive 1/2 over 1/2. And again, you know we're not going to leave it like this, plus c. Now, to not leave it like that, bring this up top. This is now 2/3 x to the 3/2. Multiply this and it's 2, right? So 2 times 1/2, if you notice, these actually will cancel each other out. X to the 1/2 plus c. And again, these are canceling each other out, these two 1/2s. You're multiplying and dividing by 1/2, they'll cancel out. This one, you just multiply by 2, it ends up as 2/3. Okay. Example 5. Go ahead and write it down. Now, anytime possible, I want to try and split this thing up. So I'm going to call this the integral. What if we split this thing to being the square root of x over x squared plus 1 over x squared? That way, I'm dealing with just power rules. I don't want to deal with quotient rules. Those are messy, but we'll get to them later. So now this is going to be 1/2 minus 2, that's negative 3/2, plus x to the negative 2 dx. And then, simple enough, rewrite it. So we have the integral here. So if I add 1 to this, we've got negative 3 halves plus 1 will be a negative 1 half over negative 1 half. Okay. Again, we'll fix that. Plus, this will be x to the negative 1 over negative 1 plus c. And then go back and fix them. So with a little bit of algebra here, you multiply by 2. Now this is negative, so we'll have to bring that to the bottom. We end up with a negative 2 on top and x to the 1 half on the bottom, or the square root of x, minus x to the negative 1. I say minus because it was negative down here. So x to the negative 1, that'll be 1 over x. Bring over your plus c. All right. Okay, let's go down to number 6. And these are really just a bunch of examples so that you can know what to do in different situations. The first thing I would do here is rewrite it to actually multiply it out, since you're only doing it to a squared. Let's go ahead and say it's the integral of, FOIL this out, you'll have 3x and 3x, it'd be 9x squared plus, what would that be? It would be 30x. And yeah, so 30x plus 25 dx. That's just me foiling that out. So that's going to be 9x to the third over 3 plus 30x squared over 2 plus 25x over 1, because this is now x to the first over 1, plus c. And lo and behold, we can actually simplify this one. We can have it be divided by 3 right here. 9 divided by 3, 3x cubed, plus 15x squared, plus 25x, plus c. And this is a perfect opportunity for you to check your work. This is an excellent opportunity to show you just how checking your work can be very useful. You have, if you wanted to take the derivative of this to get back to here, what's the derivative of c? 0. Derivative of 25x? 25. Derivative of 15x squared? 30x. 2 times 15. Derivative of 3x cubed? 3 times 3 is 9 squared. You should always be able to go back. So I'm going to put a little asterisk over here. Always check your work. It's so easy to take the derivative of this and make sure you end up with where you're at. Because if I had taken the derivative of this and I ended up with like 15x squared, I'd have said, whoa, buddy, I need to figure something out here because this ain't right. Okay. Number 7, the integral of 5x to the fourth, blah, blah. Pause a sec, write it down if you need it. First thing I notice on this one, just like up here, or excuse me, unlike up here, there's nothing to simplify. So all the other ones above it, there was something to simplify. Down here, there's not much. So let's do it. We've got 5x to the fourth, so this will be 5x to the fifth over 5 minus, we've got 8 x to the fourth over 4 plus 9 x to the third over 3 minus 2 x squared over 2 plus 7x over 1 plus c. Notice that every time I did it, I just go ahead and bring down that coefficient. That way I don't have to worry about rewriting it. These will simplify. You get x to the 5th, 2x to the 4th, 3x cubed, x squared, 7x, and c. Now I'm going to go back and check it. What's the derivative of this? I should get what's inside the integral. 5x to the 4th, perfect. Negative 8x to the 3rd, perfect. 9x squared, perfect. 2x, perfect. 7 and 0, perfect. So just a little introduction on antiderivatives. Have a great day.